All right, let's dive in. Today, we are tackling a really beautiful coding puzzle, a true classic that hides an incredibly powerful pattern right under the surface. So, picture this. You've got a long string of just zeros and ones. Your one job is to answer a simple question. What's the longest continuous piece of that string where the number of zeros and the number of ones are a perfect match? Okay, so here's the official mission. We're given a binary array, and we need to find the length of the longest piece of it that has an equal number of zeros and ones. Now, this isn't about sorting or anything like that. It is fundamentally a problem about tracking a state, in this case, balance, over time.
So, where do we even begin? Well, with a lot of these problems, the first idea that pops into your head is usually the most straightforward one.
Yeah, the most obvious approach is to just check everything. I mean, you could start at the very first number, check that one, then the first two, then the first three, all the way to the end. Then you'd move to the second number and do it all over again.
And that is a simple idea to wrap your head around, but it has a huge flaw, a real deal breaker that keeps it from being the elegant solution we're looking for. The brute force method will get you the right answer, eventually, but it is just painfully slow. For every single place to start, you're checking every single place to end. That gives us something we call O of n squared complexity. We just end up recounting the same elements over and over and over again. It's just not smart. So what do we actually need? We need a way to be smarter, right? We need to track the balance as we go, reuse the information we've already figured out, and find a way to jump back to important moments in the past without rescanning everything. And this is where a beautiful technique called prefix sums is supposed to come in.
But here's the twist. The normal way you'd use a prefix sum, it just doesn't work for this problem. Not at first. We need one tiny but absolutely brilliant change to unlock its real power.
Now, check this out, because this is the heart of the whole problem. If we do a normal running sum, where a 1 adds 1 and a 0 adds, 0, what happens to our sum? It only ever goes up, or it stays the same. It never comes back down. It never cancels out. So how can you tell when things are balanced? You can't.
And this is the breakthrough moment, the aha, the simple switch that changes literally everything. Instead of treating 0 as 0, what if we treat it as -1? All of a sudden, our running sum isn't just a counter anymore. It's a balance tracker. A 1 pushes the balance up, and now a 0 pulls the balance down. Cancellation is finally possible, and balance becomes totally visible in the numbers.
So with this new encoding, our prefix sum gets a superpower. At any point in the array, the sum is now simply the count of ones minus the count of zeros we've seen so far. If the sum is 0, guess what? It means we've seen the exact same number of both.
And this leads us to the golden rule. This is the whole key right here. If you're at some point in the array and your running sum is, let's say, 5, and you remember seeing a sum of 5 way back at an earlier spot, what does that mean? It means that for the entire chunk between those two spots, the net change was 0. You must have added an equal number of plus ones and minus ones. You just found a balanced subarray.
Okay, so with that one insight, the problem completely transforms. It's not about counting anymore. It's about tracking these sums and finding the biggest distance between two identical ones. So let's see how this builds into a perfect algorithm.
So here's the game plan. We'll use a hash map. Think of it like our memory, to keep track of the first time we ever see a particular sum. We start with a little base case. A sum of 0 exists just before the array begins, at index -1. Then we just walk through the array, one number at a time. We update our sum. If we've seen this sum before, great. We calculate the length and see if it's a new record. If it's a brand new sum we've never seen, we just store it in our memory with its location. Now, you might be wondering, wait, why only store the first time we see a sum? And that's a fantastic question. It's because our goal is the longest possible subarray. If you see a sum of 5 at index 2, and then again at index 10, that's a great subarray. If you see that same sum of 5 again at index 15, the subarray from 10 to 15 is shorter. To get the maximum possible length, you always want to reach back to the earliest possible starting point. So the first time you see a sum, that's the one that wins.
Okay, let's trace this out real quick. We start with our map having just one thing. A sum of 0 is at index -1. We hit index 0, it's a 0, so our sum becomes -1. We store that, -1 is at index 0. Next, at index 1, we see a 1. Our sum goes from -1 back to 0. Hey, we've seen a sum of 0 before. It was at index -1. The length is our current index, 1, minus -1, which is 2. Our new max length is 2. Then at index 2, we see a 0. Sum becomes -1 again. We've seen -1. It was at index 0. The length is 2 minus 0, which is 2. Our max length is still 2, and so on.
Now, what is so cool about this solution is that once you see it, you start seeing it everywhere. This is way more than just a trick for one problem. It's a fundamental pattern in computer science. By making just one single pass through the array and using our hash map for instant lookups, we get a time complexity of O of n. The space we need is also O of n for the map. This is as good as it gets. You literally cannot solve this problem faster than looking at each element one time. And there it is, O of n. We went from a slow, clunky, quadratic solution to a lightning-fast, linear one, all thanks to that one simple insight. And this brings us to the most important takeaway of all. This problem was never really about zeros and ones. That was just the disguise. The real lesson is this 3-step pattern that you can use on tons of other problems. Step 1. Find a way to encode a logical idea, like balance, into a number, like our running sum. Step 2. Make sure that encoding allows for cancellation, like our +1 and -1 did. And step 3. Use a hash map to efficiently detect when you've returned to a state you've been in before. Once you have this pattern in your toolkit, a whole class of problems just clicks into place. So I'll leave you with this question. What other problems out there that might seem complicated on the surface are secretly just about finding a repeated state over time? Thanks for watching.